started on time. Welcome, everybody. I am delighted to be introducing our first speaker of the semester, which is Professor Laura Blecha. Laura is a GILA visiting fellow here. She has been for the past few weeks, and she'll be here until Friday, sitting in the GILA tower. So if you haven't already spoken to her, you should really find her. Professor Blecher, oh my God, Professor Blecher. Professor Blecha, just back from sabbatical, I'm not used to this, there's a lot of you, is a leading expert on supermassive black hole and galaxy formation and evolution. And she did her PhD in Harvard. She was an Einstein postdoctoral fellow at Maryland and is now an associate professor at the University of Florida. So today she is going to be talking about one of her other topics, including gravitational wave sources and pulsar timing arrays. So let's welcome Laura Blecha, and thanks so much for being here.
Thanks very much, and thanks, Anne-Marie, for the introduction and also for hosting me here during my visit. It's been absolutely lovely. And yes, I'll just reiterate what she said, that I am here through Thursday. I leave on Friday. So I would love to chat with more of you. Please just drop me a line. Right, so today I'm going to give sort of an overview of some of the work that my group has been doing to model supermassive black holes in galaxies and how they pertain to gravitational wave sources and how that dovetails with some of the exciting things that are going on in the field of supermassive black holes, which it turns out is quite a lot of late. So first of all, just to introduce my group, these are my grad students and postdoc. And of course, work with many, many other collaborators as well, too numerous to list here. I will make a note that all three of these people in the top row of this slide will be on the job market this fall. So please keep their names in mind. So supermassive black holes. Let's start with a broad overview. We're talking about black holes that are not just the remnants of single stars that have reached the end of their life, exploded a supernova, and left behind a compact core of maybe 10 times the mass of the sun. Rather, supermassive black holes have masses of millions to billions of times the mass of the sun. And a small fraction of them are actively accreting gas at any one point in time. And this process releases a lot of radiation. So we see them as active galactic nuclei, or quasars. So I'll probably use these terms AGN and quasars interchangeably throughout the talk. So if I'm talking about AGN, I'm talking about black holes, these supermassive black holes that are actively accreting matter, and the matter releases a lot of radiation as it falls onto the black hole. So we see this sometimes on very large scales when the active black holes release not just a lot of radiation, but actually launch powerful outflows and jets well into the intergalactic medium. And then, of course, we also have these spectacular results from right around the event horizon of the black hole, from the Event Horizon Telescope of M87, and now the black hole at our center of our own galaxy 2, showing this black hole shadow surrounded by this ring of accreting matter that's bent by the gravity of the black hole. So we know that black holes exist because of their radiation, but then the ones that don't actively emit radiation, that are not currently active as AGN or quasars, we can still infer their presence dynamically. So this is something that recently won a Nobel Prize in physics. These groups that have been tracking the orbits of individual stars around the black hole in the center of our galaxy for decades and have shown very, very convincingly that there is a black hole with 4 million times the mass of our sun in the center of our galaxy. And for black holes that are further away in other galaxies, we can't resolve the individual stellar orbits like this. But we can look at the velocities of stars en masse. We can look at the dispersion of stellar velocities by looking at the width of stellar absorption lines and so on in other galaxies, and infer whether or not there is a peak in the central stellar velocity dispersion indicating the presence of a strong gravitating mass in the center of the galaxy. And so those are the dynamical masses of black holes that we can infer, at least in nearby galaxies. And there are other ways that we can also try to infer black hole masses that I won't get into today. So one of the surprising things when people first started to measure black hole masses and confirm that indeed pretty much every massive galaxy does have one of these central supermassive black holes was that their masses are correlated with properties of the galaxies on much larger scales than where the region that should know anything about the black hole gravitationally. So it's only the central few parsec or so that will be dominated by the gravity of the black hole. But we see these correlations between stellar velocity dispersion and stellar mass on much, much larger scales, more like kiloparsec scales or so. So this hints that there is some sort of coevolutionary process driving the growth of black holes and the stellar bulges of their galaxies. And this is just showing that this left plot here is empirical relation of this correlation, and on the right hand, a simulated correlation from a large scale cosmological simulation. I'll talk about those later. So we have some idea of some of the processes that might drive this. And one of them is likely to be this black hole feedback. I talked about the black holes radiating intensely and launching powerful outflows in jets. So this can have a strong impact on the gas content in the galaxy and thus on further star formation in the galaxy. And then galaxy mergers may also play an important role because the galaxy mergers can cause gas to lose angular momentum, flow to the center of galaxies, and be accreted onto the black hole, and at the same time fuel new star formation and dynamically grow the size of stellar bulges. Things that were, once the stars get mixed up, they're more likely to be in a more spheroidal or ellipsoidal configuration. So the other reason that galaxy mergers are very exciting is because they bring two black holes together. I said most massive galaxies have a supermassive black hole in them. And so when the galaxies crash into each other, the two black holes are going to start to sink to the center of the merger remnant via a process known as dynamical friction. And they can eventually form a bound binary. And eventually, that bound binary will spiral closer and closer together until it merges. And so this is very exciting because supermassive black holes are extremely powerful sources of gravitational waves. You can think about the gravitational waves that we see from stellar mass black holes. We've seen many, many of those sources thus far. And these are far, far more energetic events. And so we can see them from vast distances, basically across the observable universe when it comes to the actual merger. And so the ways that we look for signatures of gravitational wave sources, gravitational waves from these supermassive black hole binaries is twofold. So pulsar timing arrays, which I'll talk about in more detail later, are sensitive to nanohertz frequencies, extremely low frequency gravitational waves emitted by the most massive black holes of billions of solar masses. And pulsar timing arrays were literally looking at an ensemble of pulsars in different points in the sky and timing the arrivals of their pulses and looking for deviations that indicate the presence of gravitational waves. And then LISA, which will be launched sometime next decade, will be able to detect actual mergers of black holes at the lower end of the supermassive black hole spectrum, so less than 10 to the 7 solar masses or so. So as I said, I'll come back to more details about this later, but I can't move on without highlighting the most exciting news on this front of late, which is that pulsar timing arrays earlier this summer announced evidence for the gravitational wave background, the signature that I just described. So this is a plot of this correlation signature that we expect if these pulse timing deviations are coming from gravitational waves. So this is from the NanoGrav collaboration, the pulsar timing array collaboration that I'm a member of, as are other people here at CU. But pulsar timing arrays around the world have also found consistent results. So again, I'll come back to that more later. So we can, in addition to looking for gravitational wave signatures, we can look for electromagnetic signatures of supermassive black hole binaries. And best of all, we can look for both from the same source. So multi-messenger sources can tell us a huge amount about the physical environment of these sources, how they're produced, and even put constraints on cosmology. So black hole binaries have to spiral in through a very large range in spatial scales. On the largest scales, we can actually resolve to individual sources. As we get down to smaller scales, the evidence for these thus far has been very sparse. This is really the only robust candidate that we have at parsec scales. And then we have many, many milliparsec scale candidates where we can't resolve them directly, but we can look for signatures of variability in their light curves or in their broad emission lines that might indicate orbital motion. So this is my little schematic for where, my view at least, of how my group's work, which focuses primarily up here on galactic and cosmological simulations, fits in with the broader picture of how we aim to understand supermassive black holes. So as I described, we are hoping to get more and more gravitational wave observations of supermassive black hole binaries and electromagnetic observations of these sources as well. And then combining that with theory will allow us to develop a cohesive picture of how the various processes that drive black hole evolution fit in to the production of these multi-messenger sources and the galaxies that they live in. So I won't talk about all of these things today, but I'm going to focus on black hole formation first, and then a little bit later return to black hole dynamics in the context of gravitational waves. So this is an adapted version of this slide that I've been showing in talks for a while prior to JWST results coming out. So this is more or less where things stood before the launch of the James Webb Space Telescope. That we have this puzzle where we have a population of quasars creating massive black holes at redshifts of 6 or 7. And that makes it very hard to understand how they could form and grow to such huge masses, a billion solar masses, within the first less than a billion years of cosmic time. All right, so this has been a long-standing puzzle. How do these black holes form and grow so rapidly? So we have many, before I get to the update of what we've learned so far from James Webb, we have a number of theoretical ideas about how these black holes might form and grow so rapidly. The long and short of it is you could form little black holes and grow them very rapidly. So that's basically if you form them from the first stars that should be more massive than the stars that form in our universe today. Then we know those are going to exist. It's just a question of how you get them to grow so fast. It might require accretion at rates higher than the theoretical maximum rate, called the Eddington limit. Or you could form very massive seeds initially, which doesn't take quite as much of a stretch to figure out how you can grow them to a billion solar masses so rapidly. But then you have to face the problem of how do you get a gas cloud to collapse directly into a 10,000 or 100 solar thousand black hole seed. So there are a number of theories about how this could happen. Some of them require fine-tuned conditions. Some of the more recent theories might not require such fine-tuned conditions, but that's definitely makes it easier to solve this problem of the highest redshift quasars. And then, of course, we could imagine intermediate scenarios where we form a cluster of these early stars that might form a supermassive star and then collapse, or maybe they just form a bunch of black holes that are able to merge sequentially, avoid getting ejected out via gravitational wave recoil, and form intermediate mass seed. So again, this is all theory, and this is my very quantitative picture in this cartoon here. But as I said, James Webb has really changed this picture dramatically. Honestly, even since the last time I gave a talk about this stuff, I definitely had to do some updating of slides because the papers have been coming fast and furious. And apologies to Arthur C. Clarke for my corny paraphrasing here. But this is definitely the takeaway, I would say. The early universe is indeed full of quasars. So the record setters in terms of redshift, we have this very interesting black hole candidate at a redshift of 8.7 and another one at a redshift of 10.6. So, this is very exciting because we're starting to fill in this puzzle of where the black holes came from at those early times. But it's also putting even more tension on these models of how we can form these. So this little schematic curve here in this discovery paper is showing that if you grow the black hole at the Eddington rate, this theoretical maximum rate, maybe its descendants could be equivalent to this population of Z of 6 or 7 quasars that we observed, the ones I mentioned earlier. But still, this is very stringent. You don't have a lot of wiggle room here when you're talking about massive black holes that form this early. So that's very exciting. And now we're seeing populations of black holes in the early universe. So this is little thumbnails of these little red dots. Erica called them cute. Kind of cute. And so we can see here, there's several papers here that have been compiled in this plot showing the luminosity of these things, some of which seem to perhaps be in excess of that theoretical maximum Eddington rate, and then following this relation with the inferred black hole mass. So there is a lot that we have left to learn about these AGN. Some of them are showing very interesting compositions, and we still don't know much about their host galaxies, or whether we're seeing the actual remnants of direct collapse black holes undergoing their first epoch of growth in some of these. So it's very, very exciting. Still more very recent results from James Webb about these high redshift AGN. This one showing the relationship between AGN luminosity and black hole mass for lower redshift objects, and then also for these higher redshift ones. I won't go into the BPT diagram, but traditionally people say AGN are over here, these AGN are here, so a little bit different than our traditional low redshift AGN picture. This was a recent theoretical paper. I really like this schematic. This is the redshift 10.6 one that I mentioned, with some just sort of schematic contours for where black hole seeds might form, and then how they might grow at various rates, and how they might be able to produce the populations of black holes that we're starting to see. So this is the puzzle pieces starting to be filled in. But it's raising as many questions as it answers in some sense, because it's still a big challenge for theorists to figure out exactly how these black holes form and how to distinguish between the different models. Forming at low masses and growing quickly versus forming at high masses and not growing quite as quickly. And I like this plot from this paper by Riccardi and Natarajan a few years ago, because it, I think, shows very nicely that, if anything, the LISA event rate might be the best probe of these seed origins, right? That the difference between light seeds and heavy seeds is likely to show up strongest in the merger rate events seen with LISA. So as I said, my group focuses a lot on making predictions of supermassive black hole populations using large-scale cosmological simulations. So this includes the illustrious TNG cosmological simulations. So there's just a little bit of information there. We're talking about a volume of the universe that is run from very high redshift to today, tracing both hydrodynamics and gravity, along with a bunch of subgrid models for the processes we can't resolve directly, like star formation and feedback, black hole accretion and feedback. And they do a pretty good job of reproducing a lot of the empirical observations and relations that we have about galaxy populations over cosmic time. But they're not perfect. And one of the things that we don't have a good handle on is the seeding, right? Because of the large volume of these simulations, we can't resolve those low mass seeds, or even really the formation of the heavy seeds. And these environments are very dynamic, and this is the assembly of a massive galaxy at early times. And you can see how there's just streams and clumps of gas falling in constantly, and occasionally larger mergers. And so I like to show this to illustrate why cosmological simulations have a valuable role, in addition to semi-analytic models, which start from, say, a dark matter only framework or an analytic framework, and are able to much more efficiently probe large parameter spaces for all these unknown parameters, but can't resolve the detailed inner structure of the gas and stars in these galaxies. So that's where this type of work fits in. So I'll just start by highlighting this work by my student, which is, I think, going to be submitted by the end of the week. So she has developed sort of a hybrid approach where she's using the illustrious TNG simulations and then building a semi-analytic framework on top of that to probe seeding environments that were not part of the initial illustrious simulation. So in these simulations, there are just massive seeds formed according to a very simple prescription. But Annalise's framework allows her to pick seeding sites based on whatever gas and halo properties she wants, and say, well, that's where a seed formed, and now I can trace it through the merger tree, galaxy merger tree, and see what sort of black hole population I would have ended up with if I would have seeded a black hole in there. And so this is just showing there's actually a pretty good convergence of the black hole mass densities as you get to lower redshifts, but still a wide range of models, including some that are already in tension or completely ruled out by high redshift quasar observations, but others that overpredict the population region that we see so far. So I think this is a promising way forward for sort of taking some of the advantages of both of these approaches and combining them. And then Aklan Bomek, postdoc at UF, has been leading this large effort to develop new seeding prescriptions to directly implement in cosmological simulations. And so this is using primarily cosmological zoom in simulations. So that allows us to get higher resolution on sort of one galaxy environment, one galaxy halo. But the trade-off is that since it's not a uniform resolution volume, we can't as easily make statistical predictions about, statistical statements about how common such and such a feature is per unit cosmic volume. But so he's done a systematic study for this variety of black hole seeding criteria that are based on what we think is important for our seed formation theoretical models. So metal poor gas, low metallicities will help gas to collapse monolithically without fragmentation into small clumps. And having it close to the density where it's going to start forming stars is also going to be important. Make sure you have a collapsing cloud. And then we can also put criteria on the seed masses, the total halo mass, the angular momentum, and so on. And so one result from his initial paper on this work that I'll highlight is that there seems to be a transition in the relative importance of the halo mass and the gas mass, the star-forming metal pore gas mass criterion. So when we vary the halo mass, we see that it makes the biggest difference in the black hole merger rate at the highest redshifts, whereas varying the star-forming metal pore gas mass criterion has a bigger impact on the merger rate at slightly lower redshifts. So there's sort of a transition in when that becomes important. And then he has also used constrained initial condition simulations. So if you want to simulate rare, extremely massive galaxy halos, generally you have to simulate a very large volume because they're rare. But that's expensive. And if what you care about is simulating that massive halo, then it would be nice if you could pick a small volume and impose on it initial conditions that would be predisposed to collapse into a massive halo. So that's the idea here. And so in this work, he explored the formation scenario channels for massive Z of 6 quasars. So seeing how we can get something to around 1 billion solar masses by Z of 6. And so you can see that there's a lot of similarity between the results for varying some of these parameters. And so this is, again, where these new results from GWC are going to be really important for teasing out the differences at higher redshift along these growth pathways. And in particular, one feature of these models is that they are very highly merger dominated in terms of black hole growth until about redshift of 8 or 9 when gas accretion really turns on. And so and this is in part a feature of the accretion model we're using, but there's a lot we don't know about how gas accretion really works on these early black holes. So again, this is the kind of thing that we can start to put constraints on with these high redshift observations. So I will, before I move on to the second part of the talk, I want to highlight the most recent work that he's developed here, which is taking these Zoom simulations, these high resolution simulations, and with these seed models that are directly resolving these low mass seeds down to almost 1,000 solar mass seeds, and then tracing those, their evolution, up to the point where they form more massive black holes that could be resolved in a lower resolution simulation with larger volume, where we could start to make statistical predictions. And figuring out what the properties of the halos are that would contain those more massive descendants of the unresolved seeds. So that's the idea here. And so this is just showing that we started with matching just the halo mass distribution. And impressively, it turns out that we were able to match a number of other important properties: stellar mass, star formation rate, gas metallicity, their distributions, just based on matching the halo mass, which I was certainly surprised at how well this worked. But it didn't get us all the way there because it doesn't reproduce the environment of the black hole, the richness of its environment, the number of nearby neighbors of that black hole formation site. So Oakland has developed a probabilistic formalism to match the environment and in a framework that doesn't reduce computational efficiency, so it's still tractable from a numerical standpoint, that reproduces the environment, the two-point correlation function, merger rate, and a number of other properties. So I think this is really exciting because we now have these calibrated models that can reproduce black hole populations that are seeded at 10 to 100 times higher resolution, and in these lower resolution simulations using only a few properties of the halos that are relatively easy to measure on the fly in simulations. So halo mass, redshift, environment being the big ones. So I think this has a lot of promise for the future of physically motivated seeding in these large simulations and the gravitational wave and AGN predictions we can make from them. So stay tuned for that. That paper should be out relatively soon. All right, so for the rest of my time, I'd like to talk about black hole dynamics, particularly in the context of black hole mergers and gravitational wave sources. I'm actually not going, usually I talk at least make a brief mention of kicked black holes, which I won't today unless someone asks me about it. But there's lots of exciting stuff happening just in the space of black hole binaries. So as I said at the beginning, there's a very large range of spatial scales that is spanned by a black hole pair that starts out each in its own respective galaxy as these galaxies come together and merge, and then the black holes are falling towards the center of the merged nucleus until eventually, at much smaller scales, they form a gravitationally bound binary. And then, even then, they still have to spiral in through many orders of magnitude before they reach the regime where gravitational wave emission will dominate the loss of orbital energy and drive them efficiently to merger. So the details of this are somewhat uncertain, both from an empirical perspective, because as I said, resolving these really small scale bound binaries is difficult or in some cases impossible. And we have to rely on indirect signatures. And then from a modeling standpoint, it's also challenging because we have to be able to model both large scales and very small scales and everything in between. And so that's not an easy task. So that results in a lot of uncertainty on the in-spiral timescales, how long it takes a binary to go from this initial phase to an actual merger to a gravitational wave source. So I'm going to highlight here some modeling results from the Nanograv collaboration. We've recently developed this software dubbed Holodeck for binary population synthesis and parameter estimation. And so what's being shown here is the in-spiral timescale at a given separation versus binary separation. And so it starts on this plot. Large scales are here and small scales are here. And so at the smallest scales, we have gravitational wave emission. So it's a very well-constrained slope here for that region. But then this part is where a lot of the uncertainty is. And so in this particular set of models, we're making an assumption about the efficiency of in-spiral at the largest scales, and then making a different set of assumptions about the efficiency of in-spiral at these scales, and testing 3 different models varying the efficiency of that sort of parsec scale in-spiral. And if you follow this field, you might have heard of the final parsec problem, because there is a lot of uncertainty here for various reasons about how efficiently this in-spiral might proceed. But yeah, I'll gloss over a lot of those details, because that's a whole other talk, potentially. These black holes, as they're spiraling in, they emit gravitational waves the whole time, right? But the gravitational waves get stronger and stronger as they get closer. And so at very, very large separations, the gravitational wave emission is going to be more or less negligible. But as we get closer and closer, you're going to see the gravitational waves at a particular frequency from a particular binary. And since there are tens or hundreds of thousands of binaries emitting gravitational waves that we could potentially detect in our local universe, the cumulative effect of these is that we get this gravitational wave background spectrum of unresolved binaries, each emitting their own frequency, that are combined into this broken or turnover power law type model. And so that's what's being shown here is the gravitational wave strain from all of these binaries, each emitting its own frequency and its own redshift. They're not going to evolve in separation space much on human timescale, so they're essentially fixed sources from our perspective, unlike LISA sources. This is the kind of spectrum we expect. I will note this dotted line here is the expectation from gravitational wave emission only, whereas the colored lines are when you incorporate these models here for the astrophysical processes, the stellar and gas dynamical processes that are driving the black holes together at those large and intermediate separations. And so there's a couple of things to note here. One is that those astrophysical processes cause attenuation of the gravitational wave background spectrum at these lowest frequencies especially, because the interaction with the stellar and gas environment is driving those black holes through those regimes of frequency space faster than gravitational wave emission alone would. And the other thing to note is that the dotted line, the gravitational wave emission only line, is not a power law. So a lot of the predictions for the gravitational wave background spectrum use just a smooth power law. And that's what you can do an analytical prediction for what you expect if gravitational waves are the only thing bringing the black holes together. But that simplistic prediction ignores a couple of things. First, that orbits might not always be circular. And so eccentricity of binaries can change the shape of the spectrum. And also, when you get to these highest frequencies, the timescales for those black holes to move through that frequency regime is much shorter than at the lower frequencies. So the closer they get, the faster their in-spiral starts to proceed. Which means that sources here are rare. They spend less time here than they do here. And so you actually start to run out of enough sources to have a smooth background, and the actual discrete nature of the sources producing this smooth background becomes important at the highest frequencies. All right, so this is another really nice illustration from the Astro Working Group paper from the recent Nanograv data release that I'll talk about the actual data more in just a minute, but I want to talk first more about the physics of the sources that are actually producing these gravitational waves. And so this is a bunch of models similar to the ones I just showed, and the gravitational wave background spectrum that is produced as you vary different parameters in the models. Yeah, I think this is the most recent, the actual version that was in the paper. Apologies in advance to Joe if it's not. No, I think it is. So anyways, basically we're varying here the time scale, the total time scale for the merger, the parameters governing the galaxy solar mass function and merger timescales, and the black hole galaxy scaling relations. And so you can see that as we change these different parameters, we can turn these knobs and get very different shapes and amplitudes for the spectrum. So the point being that we can, if we measure the spectrum robustly enough, learn a lot about the underlying supermassive black hole population. And then also, this is very important for inferring the population of black hole mergers that we expect to see with LISA once LISA launches. So let's see if I can get this movie to play. This is a great animation that was produced for this recent press release showing where the array of pulsars is relative to the Earth in our galaxy. And so you can see here this ensemble of pulsars at different places in the sky that are all spinning with several millisecond periods and emitting very regular pulses. And so then we can detect, as I said, the arrival times of those pulses and look for deviations in the arrival time that would occur when gravitational waves pass between the pulsars and Earth, either delays or early arrivals. And so the signature that we expect to see, which I showed the plot of earlier, is this so-called Hellings and Downs correlation. And the idea here is another great animation, that when the pulsars are separated by small angles on the sky, then you expect to see a correlation between the pulse arrival times, like so. When they're far apart, or where they're more like 90 degrees on the sky, then they're going to be anti-correlated. Let's see if I can get that to play again. And then once they're closer to 180 degrees apart on the sky, they're again going to have deviations in the same direction. So this is the signature that we're looking for that says that any timing deviations we're seeing is actually coming from gravitational waves and not something else in our data that we don't understand. And I do, before I show the Hellings and Downs result again, I do just want to highlight that we didn't just see the Hellings and Downs curve and put it out there and say we detected gravitational waves. We have been seeing evidence of a gravitational wave like spectrum in our data for a while now. So this is from the 12.5-year data. So we were already seeing something that looks like a gravitational wave background back then. We just hadn't seen significant evidence of the Hellings and Downs correlation. So now we're still seeing this gravitational wave background at even greater significance. And we have now found evidence for the Hellings and Downs correlation, as have other PTAs around the globe, including the European Pulsar Timing Array, the Indian PTA, the Parkes, and the Chinese Pulsar Timing Array. So this is, as I said, this recent data release showing strong evidence for the Hellings and Downs, indicating that these timing delays we're seeing from pulsars are indeed produced by low-frequency gravitational waves. And then we can't say for sure what is producing those gravitational waves, but certainly supermassive black hole binaries are a likely candidate. And since we know that supermassive black hole binaries have to form in the universe, then if the signal is coming from something other than binaries, then that raises the question of why aren't we seeing what's going wrong with our understanding of how supermassive black hole binaries form and evolve. So this is, as I said, the gravitational wave background spectra. So this is the nanograv 15-year result, and then the results from the other collaborations. So as you see here, these are fit with straight power laws, but we also did analysis looking at what happens if you fit a more astrophysical model that has a spectral turnover due to a interaction between the black hole binaries and its environment. So this here is showing the best fit amplitude and spectral index for the nanograv 15-year data, calculated two slightly different ways here. So that's the green and the gray contours. And then the purple contours here is what we get when we use our binary population synthesis model, assuming only gravitational wave in spiral. So again, that's not, if we just use gravitational wave in spiral, it's not necessarily a straight power law, but we're not assuming interaction with the environment. Versus the blue curve here, which includes our models with all those parameters that were being varied before, the best fit posteriors to those parameters for the coupling of the binary to its astrophysical environment. So one thing you might note from this plot is that these contours are huge. So we're not really in the regime yet where we're strongly constraining binary parameters. But it's definitely, I think, very promising that we have this framework where we are able to quantify the uncertainty. And also, one of the interesting things is that there's a little offset in the centers of these contours. So the data, if we are slightly favoring higher amplitudes and slightly lower spectral indices than our sort of naive model expectations. And as indicated by these little arrows here, that is potentially indicative of more or stronger coupling of the black holes to their environment, and or more massive black holes, or simply more binaries than our naive expectations. So that's very exciting in and of itself, even though it's still a tentative result. And then this is the same color scheme here. So we have the gravitational wave only in purple. And then here we have blue and orange, two different flavors of the astrophysical coupling model. And so first of all, the results are consistent with these model spectra. So it's consistent with the population of supermassive black hole binaries. As I said, we are finding hints that black hole binaries are more numerous and or more massive than expected. And it also looks kind of like the spectral turnover models, the blue and the orange, are slightly favored by the data. That's not a strong quantitative statement at this point, but we're seeing possible hints of an attenuation or turnover in the low frequency gravitational wave spectrum, which could very well be evidence of coupling with the gas and stars around the black hole binaries. So this is very exciting, and I just want to emphasize again the potential for continued observations to really pin down the shape and amplitude of the spectrum. And so, you know, a lot of the cynical take on this gravitational wave background detection effort was, oh, well, you're just looking for two numbers, amplitude and spectral index, and then you're done, so you can all go home. No, this is just the beginning. This has just launched a whole new era, low frequency gravitational wave astrophysics. We have the potential to learn a ton about the supermassive black hole binary population. And if it's not supermassive black hole binaries, then probably we have some potential to learn about fundamental physics that we don't understand yet from the early universe. And we also have the potential to observe individual supermassive black hole binaries. So this is a schematic from a theoretical model by Luke Kelly from several years ago, showing so there's some fits to these realizations of the gravitational wave background from his models, and the dots are the individual sources. And you can see that there are some that are popping up way above the background. And so if you have enough signal to noise, then you can start to resolve out these loud sources above the background. And again, since I said these supermassive black hole binaries are not going to move significantly in separation space on human timescales, they're essentially going to be just spikes at that frequency. So we refer to them as continuous wave sources. So we have promising prospects for detecting these continuous wave sources in the coming years. How quickly that happens does depend on just how lucky we are in terms of the universe that we were given. If there happens to be a very nearby source or sources that are very loud, then we might detect it very soon. Otherwise, we might have to wait a little longer. But either way, this is going to be a very exciting method for trying to understand black hole binaries. I want to highlight this result from a recent paper by Joe Simon, showing, so this is basically showing predictions for continuous wave source observations. And so he's showing here that whereas this model shown in orange here with a more standard approach to making these estimation really favors the lowest redshift sources. This blue curve here, this alternate calculation, is showing the potential for continuous wave detections from higher redshift sources, which greatly increases the volume of the potential discovery space. And again, the holy grail for gravitational wave astrophysics is to also detect electromagnetic waves from the same sources. And so this is going to be a really exciting prospect. And one of the nice things about these continuous wave pulsar timing sources, as opposed to, say, LISA sources, is that these things are going to stick around. So it's, as opposed to a transient gravitational wave source, it's not going to be easy to localize where these are coming from, but they're also not going anywhere. So we're just starting to scrape the surface of figuring out the best approach to looking for the electromagnetic signatures from the counterparts to any continuous wave sources we detect. All right. So with that, I'll go over just sort of a broad summary. LISA and James Webb will provide much needed constraints on black hole formation mechanisms, and James Webb already is, arguably. But we need theoretical models to differentiate the observable signatures of various seeding channels and actually be able to disentangle the underlying physical mechanisms at work. And then additionally, we still have significant uncertainties on black hole binary in-spiral timescales. And these depend strongly on the astrophysical environment. It's a highly non-trivial problem for theorists. But pulsar timing arrays have found evidence for this gravitational wave background that is consistent with the population of black hole binaries. So we hope to get constraints on this population in the near future with continued pulsar timing observations, and hopefully with continuous wave sources. So the future of low-frequency gravitational wave and multi-messenger astrophysics is bright. I'll leave it there. Thanks.
Thank you so much for that great talk. We're going to continue our tradition of having the first question be from a student. Hannah-Laura? Right, so the question is, can we use LISA merger rates and merger event properties to understand the seed formation channels? Yeah, yes, so that's exactly the hope, is that LISA is going to be able to disentangle. Obviously, if we start to see LISA sources, a bunch of mergers between, less than 10,000 solar mass black holes, or if we only see a smaller number of more massive mergers in the early universe, then that's going to start to indicate, which way the balance tips. But in reality, we're probably going to have to do some more sophisticated parameter estimation with our models to be able to say anything quantitative about, which seed formation channels are favored and how strongly. But yes, that's the idea. Questions?
If you have some candidates with a few year periods, how much does that help you in finding these things in the background?
Okay, so like if you have periodically variable AGN that have periods of a few years, how does that help you to identify continuous wave sources in the background? It's a good question, and I don't have an answer that's not super hand-wavy as of yet. So, I mean, I think obviously that kind of targeted selection of potential host galaxies is going to be important. I mean, so what we know about potential...
Period and direction.
You know period and direction, right. But if you have, say, hundreds or thousands of potential galaxies in your error region, how do you say, you could say, well, I have this periodically variable source, the period seems to match, it's in the right place in the sky. I would say that's certainly a very strong candidate, but how do you get from there to saying it's definitely not one of these other galaxies that just doesn't happen to, that's where we need to do a lot of work on the theory side to be able to make really quantitative statements. But yes, the periodically variable candidates are going to be super important for at least trying to start narrow down the galaxies.
I was wondering, so if I understood your more careful astrophysical modeling of the, it's not just two numbers, there are these secret additional parameters that we take care of.
They're not so secret, it's in the paper.
Okay. So when you showed that plot, you had your larger contours, presumably because there are big uncertainties on those things behind the scenes. But does the detection inform any of those other secret quantities? Like if you look at distributions of those, are you exploring the entire parameter space, or are there some weird corners of astrophysics that we can already rule out?
Yeah. So so the statement here that we're finding that binaries are more numerous and more massive than expected. Quantitatively, what that means, and I can show you the whole corner plot later if you want. Quantitatively, what that means is that shorter total in-spiral timescales are favored. So the binaries are getting to that gravitational wave regime efficiently, and more massive systems are favored. So that's either a higher, let's go back to this. Right. This is normalization of the galaxy stellar mass function. This is the turnover mass. And then we have normalization and scatter of the n-sigma relation. And so basically, any combination of those that boosts the total mass of supermassive black holes that are in binaries is going to be favored by the models. But aside from those two statements, the masses and the n-spiral timescales, everything else is very weakly constrained, meaning it follows the priors. So sorry, it's a little bit painful. The two different flavors here in orange and blue are using uniform versus astrophysically based priors. And so, everything besides those two things I mentioned just follows the priors.
So it's totally fine if this is too open-ended and we just talk about this later, but so it makes a lot of sense how you use these supermassive black hole binary mergers to constrain formation. I'm curious, are you familiar with anyone using mergers from failed seeds that did not end up because supermassive black holes did not end up having their own galaxies, probably because they're related merging? Because my understanding is that intermediate mass black hole mergers should be at the upper end of the Blecha band.
Absolutely. Sorry, was there?
So yeah, my question is just, are you familiar with anyone working on that? Is that something you're interested in?
Absolutely. So yes, the mergers at the earliest stages, then we expect to see mergers at whatever black hole masses are there. It's just a question of how efficiently they come together and merge. And the way you framed it in terms of failed seeds, if you have a black hole that doesn't end up staying in the center of galaxy, maybe it gets kicked out, or just dynamically doesn't end up in the center of a protogalaxy. it's less likely to interact with another black hole, just because things that end up in the center of the gravitational potential are much more likely to interact with each other. Yep.
Okay, so we are at time. So we'll stop here. I do want to say that we have one more spot for dinner at 6 p.m. So just let me know if you're interested in joining us and talking further to Laura. And let's thank our speaker again for a great talk.